Alright, so in this video we're going to take a look at an example related to the torque speed characteristic that we introduced recently. And essentially what we're going to do is we're going to compare the acceleration of the vehicle, or a vehicle, under two different, modes of operation. So in the first case we'll look at the constant force acceleration. That's just assuming that there's a constant force and we're applying it and we're trying to get to some steady state speed. And in the second part of the example we'll apply our torque speed characteristic where we have a constant force and then we start to decrease the force as the speed increases, and instead we maintain a constant power. So the example says we assume an equivalent mass of 1,000 kilograms and an acceleration time of 10 seconds from standstill, and we want to reach a speed of 25 meters per second. We're ignoring all forms of resistance and we need to determine the power requirements of the motor. So in the first part, let's look at that first. So we have the constant acceleration, so let's say part A. So the constant force acceleration, I should say. So during acceleration, so we can say during acceleration, what do we have? We have that the acceleration dv by dt is equal to the final speed minus the initial speed divided by the time it takes to reach that final speed. So the acceleration will be 2.5 meters per second squared, since the force is going to be kept constant. Constant force means constant acceleration. So what is the force, actually, if you were to want to achieve this acceleration for the given mass? We know from Newton's law, we have that the force is equal to the mass, in this case it'll be the equivalent mass, times the acceleration, right? So this mass is 1,000 kilograms times 2.5, which is 2,500 newtons. Simple enough. Next we have the power. So what power do we need to exert this force for this to reach this speed, right? So we have, this will be 2,500 times v, right? And in the, in the maximum case, you would have 25 as your speed, right? So once you get to steady state speed, you'll go, let's say PT max will need to be 2,500, and the fastest we want to go is 25, meaning the maximum power you'll need is 62.5 kilowatts. Now if you want to go down, so during deceleration it'll be the exact same thing, but it'll be in the opposite direction. So I guess we can also say and deceleration here, and maybe we can make a little bit of a note here and say negative power and force for deceleration, right? So you need to have the force in the opposite direction if you're slowing down, obviously. But the idea here is that the power will increase from 0 all the way up to a maximum of 62.5. And of course, when you're cruising, the speed is kept constant. So now we can, I guess, imagine what this looks like. We shouldn't go that far down. We can imagine what this looks like in terms of a sort of profile, I guess. So if you want to imagine, we can draw these things out and we can start to think about what does this actually represent in reality. So in reality we have the following. Let's say we decide we want to plot something related to the speed, let's say. So if the speed, let's say we'll break it up into sections of 3. This is nothing unique. It doesn't have to be 3, it could be 4. It's just a division, I guess. And so if we call this first thing the speed, so if this is the speed, then what you're going to have is the speed will increase linearly up to some maximum. And then let's say we want to cruise for a bit, and then we want to decelerate after that linearly, right? So this is all constant force acceleration / deceleration, and then we'll go down to 0. So the maximum speed that we want to reach here is 25 meters per second. Now what's going to happen for the, let's say, the force? So this is the force. What will happen to the force for during this time is that we'll apply a constant force during this time. When there's no when you're cruising, I should say, you'll have, that should not go all the way down. We should stop at 0 here. Stop at 0. So 0 force when you're cruising, because the speed is constant, all the forces are constant, we're assuming there's no resistance. And then when you're decelerating, you'll need to apply negative force. Then I went 1.5 there, so let's go 1.5 here. like so. And then when you come back to a standstill, you're at standstill. You don't want to keep going in the negative or the reverse direction, so you go back to 0 force. And this is going to be 2.5. Maybe we can write here the units and say kilonewtons. And they make that 2.5, and then we can make this one here. This is minus 2.5 kilonewtons. Well, we've already written the units, so I don't need to write that again. And this speed will be in meters per second. And these axes are time axes here, in seconds, of course. And then the last thing we can look at is the power. So the power is the product of the speed as well as the force. So you would expect then that this would increase following this type of profile. And then during this time, the product is 0, so it would drop down to 0. And then the product would remain 0 during this time. And then it would drop down to a negative power. And then it would go back up to 0, like so. And this is 62.5. And this is minus 62.5. And this is the power. So we see we have a certain type of profile here. So I guess this is acceleration, this is cruising, and then this is deceleration in the third region. So now we're going to move on to part B. And I guess one detail that I missed before I move on to part B is to say that this is 10 seconds, right? And I guess this is also 10 seconds. And if we're going to keep everything to scale, then this is also 10 seconds. But that's not an important detail of the example. The 10 seconds is, but the cruising part, I guess, is not. So you want to be able to reach this in 10 seconds is the important part. And then also decelerate. If you accelerate in that much time, then you would obviously decelerate in that much time as well. So now in part B, we're going to look at a more interesting implementation of this. So part B, we're going to revisit our torque speed or force speed, and the two are interchangeable really, because remember, the torque and the force are interchangeable simply based on the radius of the wheels. So you have a certain, let's say, power that increases like this. We call this power. And then you'll have a certain force that varies something like this. And remember, we draw these two on the same plot, but they are by no means necessarily crossing over and equal to each other at that point. So this is, I guess you can say, force and power here. This is your base speed. They say that the base speed should be 10 meters per second. They say that the maximum force is, in this question, 3625. So 3625 newtons. And this is obviously your speed here, and this is a linear speed in meters per second. So now what we want to do is we want to first determine how long does it take for our vehicle to reach our steady state, or sorry, not our steady state speed, our base speed. Because once we determine that, then we know at which time we cross over from the constant force into the constant power region. So how do we do that? So we can say here, so let's say for 0 to 10 meters per second, you have Ft equals 3625, right? Now if we write Newton's law, then we have 1000 dv dt equaling 3625. So we know that the acceleration during this time is 3.625 meters per second squared. Now using this, we can determine the time that it takes for this thing to happen. So if we bring it over here for a second, we solve an integral, and we can integrate both sides, and you can get v equals 0 to v equals 10 dv equals 3.625, and this is from 0 to t1, we'll call it. And t1 is the time that it takes to get to 10 meters per second. If you solve this integral, you'll find that t1 equals 2.76 seconds. Now that means that it takes the vehicle 2.76 seconds to reach the base speed of 10 meters per second from a standstill. Cool. So what's the next thing we can look at? So the next thing we can look at is, let's verify, okay? So we need for 10 to 25 meters per second, we have the constant power of 36.25 kilowatts. Okay, now how do we get this constant power? We get this constant power based on the force as well as the base speed. So if you look at your plot here, since these plots are continuous, or this plot is continuous at this point, then PT max should be equal here to VB times this force, right? That's sort of the condition. So if we know in general that PT equals FT times V, and at VB, FT equals 3625, then the tractive power at that point must be the product of the base speed as well as the maximum tractive force, right? So that's where we get this from. So we say 10 times 3625, and we get this number here. So next we can say that during this region, we have that the force should decrease based on this requirement, right? So I guess this is equal to Ft times V, meaning Ft should equal 36,250 divided by V, right? So it should decrease as the speed increases. This is our profile, right? We said that this force decreases inversely proportional, or I guess it increases. Well, I guess it decreases in proportion as the speed increases, right? So as this V increases, it should decrease, which is exactly what this expression here shows us. So if we want to look at, I guess we can verify T2 or to make sure that we actually meet the requirements, we can look at just a little extra step here. So we can say that if we want to go from 10 to 25 meters per second, and this is V times dV, and you will have on the other side 0 to T2 dt, and if you solve this, you'll get that T2 is equal to 10 seconds, which confirms that we can do this in 10 seconds, right? So it may be such that in the first case we were able to achieve 10 seconds, but in the second case we weren't. But this example was designed specifically to do that, but this is just a verification of that, I guess. And the last thing I want to look at before we kind of summarize everything in a plot and sort of compare the differences is this idea of the maximum tractive force, right? So let's say Ft max. Well, not Ft max. I don't want to call it max because that's not max. Let's call it Ft steady state, right? So Ft steady state will occur at, let's say FTSS equals Ft evaluated such that V is equal to 25, right? So that means you take this expression evaluated at 25. So this is 36,250 divided by 25, and that gives you 1450 newtons. And this is an important number to sort of be aware of, because we're going to look at some, we're going to look at a waveform actually in a second, and that waveform will, or these waveforms are analogous, or I guess they're comparison, they're not analogous to, they're a direct comparison to the ones we looked at in the first part. Let's take a look at those waveforms then. So we're going to do the exact same thing. We're going to plot the different quantities, the force, the speed, and the power. And we're going to want to look at how the two, or how the three, I guess, are related to one another. And I guess this should be far enough. Always important to make sure your axes are reasonably displaced from one another, such that you can draw the accurate waveforms that you need to. And now we've gone too far down. So this one again will be speed, and this will be in meters per second. This is the force, and this will be in kilonewtons, and this is the power, and this will be in kilowatts. So what do we want to do? We want to first, let's divide it up into little sections of 3 like we did last time, just so that it's a close of a comparison as we can get. And so in the first case, what I want to do is I want to start from 0, right? So I start from 0 here. And what I'm going to do is I'm going to increase linearly like that. And I'm going to imagine for a second that this is 10 meters per second, right? So we have a linear increase from 0 to 10 because we have a constant force from 0 to 10, right? So if we have a constant force from 0 to 10, then we can say that this thing here is constant force, right? And I guess I'll mark this off with a second color. That is your time to the base speed, I guess. So we can call this, we solved this was 2.76, which means that this is 7. Maybe we shouldn't do that there, I guess. Well, so let's just extend this. So say that, well, why don't we do it here? Say that this 7.24 seconds, right? And that's just the difference between 10 and 2.76. Anyhow, you would then increase to a total speed of here, which is 25, but the increase here becomes curved like this, right? So it's not linear anymore. So this part is linear, this part becomes curved, then you would be constant at that. And while this part is curved like this, remember the force has to decrease, right? So the force has to decrease in proportion to the increase of speed. So the force is inversely proportional. And at this point, you have your FT max, which we said was 3.625 kilonewtons. And then at this point, you'll have the value we solved for, which is 1.45, if I'm not mistaken. And at this point, since you have this constant speed or zero acceleration, and this should be flat. This looks kind of like it's not, but this should have reached 25 before it enters that second region. Then you'll have this goes down to 0, and this stays at 0 during this time. And of course, we can determine what the power looks like during all of this as well. The power here will increase linearly to some maximum, because remember, it's the product of these two. And it will remain at that maximum once you've reached that speed. And it'll stay, well, here now it becomes 0 because it's the product of these two is 0. And then it will stay at 0. And now, during this time, what we're going to do is we're going to do the opposite, right? So when you're decelerating, you have to do the opposite characteristic. So this will take 7.24 seconds to come down. It'll come down here, and then this part will be linear. So we know that the last little bit between 10 and 0 will be linear. And this part here will be curved. And I hope, well, maybe we can just make a note and say this is linear. And this is linear. And these parts are not. This part is flat, this part's not linear, this part's not linear. This part, I mean, is not linear. I'm not sure how if my cursor shows up in the recordings or not. Anyhow, then, right, so the force. What does the force do during this time? So if you're going negative, you have to have a negative force. And then you have to go up to some negative force here. Well, sorry, not there. It's too far off. You have to go to the negative force here. Maybe extend this all the way down, just so I don't confuse myself, which would confuse you, which is never good. So you go here, and then you're going to make the force more negative in this direction. Apply your maximum constant negative force during that time. And then once you get to 0, to prevent yourself from going in the reverse direction, you want to decrease the force to 0 and then keep the force at 0. Otherwise, you'll keep going backwards, which is not a good idea. Here, this force will go, this power will go negative constant, and then it will linearly increase like so. This power here is 36.25. This power here is negative 36.25. Now let's directly compare this to the previous case. In the previous case, I mean, it was much simpler characteristic, that's for one. But what else? What else we should note is that, for one, this force is larger. Okay, so now you might argue that, hey, in this case we only had a 2.5 kilonewton force, and in this case we start off with a 3.625 kilonewton force. So we need more force here. Yes, you need to apply or exert a larger, or your motor needs to apply a larger force. However, the power requirements are minimized here. So this is a 36.25 kilowatt maximum power, whereas this was a 62.5, right? So it's close to double, I guess. And so what you've done by using this mode of operation, or this regime of operation, method, whatever you want to call it, you've decreased the power that you need. So you need 36.25 kilowatts. Let's say you want to give a 20% margin, you would need like 45 kilowatts, let's say, in this case. And in this case, if you want to have a 62.5 and then you want to give like a 20% margin, that would be close to like 75, I guess, ish. 75 kilowatt motor in this case versus a 45 kilowatt motor in this case. You would reduce the cost of everything. You would reduce the power requirements, the energy requirements. All your power converters will operate at lower power levels and such. So that's one of the benefits. I mean, that's the main benefit of this, is that we saw in the previous lecture video that there was certain forces dominate at lower speeds, and so this is accounting for that and making sure that you don't waste any more power than you need to. So that's it for this video. I hope this was helpful. If you haven't already, hit that subscribe button to support the channel, like the video, leave comments below if you have any questions, and we'll see you in the next one.